Hey everybody, let's give this problem a try. So we have some cylindrical grinding wheel. So I brought this in from the table in the book for the moment of inertia. Okay, and then let's see. So there's some electric motor providing some kind of torque. Okay, so there's that cylinder and there's some torque. I'll say torque from the motor. Okay, so Newton's second law for rotation. Sum all the torques acting on this grinding wheel. It's just the one, the torque from the motor, equals I alpha. The moment of inertia we can get from right there. Okay, so we don't know this, we don't know this. So we need one more equation. Let's see. So we're given information such as the angular velocity and the number of revolutions. So that is kinematics, right? So for all the formulas you know from kinematics, what would be most useful? I think, for example, right? Like, how about this one? Maybe. How about this one? Yeah. If you combine these two, then you have this other one that looks like this. Yeah, I think this is the one. Because it starts at rest, and then the final is given over here. The number of revolutions right here, and then the angular acceleration is unknown, but then it's unknown over here too. Okay, so I think that's it. So we have this one and this one. Never mind these. Okay, so these two equations. So equation 2 only has the one unknown, so let's solve for that. Alpha is omega squared over 2 delta theta. And then we can plug that in right there. Okay, so let me rewrite equation 1. Torque from the motor is I alpha. I is, from over here, 1/2 mr squared. Alpha is, from right here, omega squared over 2 delta theta. Delta theta being the angular displacement. Let's see. I guess that's it. Looks like we have all the numbers, right? So just plug in the numbers. Half mass is 50 kilograms. Radius is, they're not meaning to be tricky. They give us the diameter, so just be careful, right? 0.5 meter radius. They're not purposely tricking us, but just be careful. Okay, the angular velocity is somewhere. Oh, here. 120 RPM. Why do they keep giving us RPM? 120 revolutions per minute. Just be careful. 2 pi radians per revolution. 1 minute is 60 seconds. So this altogether would be radians per second, and just be careful, it's squared. This squared. Okay, and then there's stuff in the denominator. 2, and then the angular displacement, which was 20 revolutions. What would that be in radians? There are, again, 2 pi radians per revolution. Right, so then everything is in SI units. Okay, so plug that in the calculator and you're going to have something, 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 Newton meters. Okay, done. No, not done. There's part B. Okay, hold on. Okay, part B. Okay, so now there is a tool with kinetic friction. Oh, okay, I see. All right, so here's our cylinder. there's some motor torque, which is unknown, but now we're like pressing a tool against that grinding wheel. So if we press down on the grinding wheel, Newton's third law, there would be an equal and opposite force. So there would be a normal force normal to the surface, and then there would be friction. If the wheel is rotating kind of this way, then the friction would be opposing the motion like this, kinetic friction. Technically, the grindstone has weight, right? So there would be weight. Okay, so let's sum torque about the axis of rotation. So then the weight doesn't provide any torque about the axis of rotation. Okay, so sum torque, torque from the electric motor, which would be, let's call clockwise positive. So then this would be positive. But then the torque from the normal force would be 0 because it's aligned with this axis of rotation, so it doesn't provide any torque about this axis. There would be torque from the friction, which is this far, which is R, which is in the negative direction, right? Because the torque from the friction would be going this way, which is in the negative z direction. R, F, K. Okay, that's it, equals I alpha. And then we also know that kinetic friction is mu k times n, right? The coefficient of kinetic friction times the normal force. Okay, and then we also know that the moment of inertia was this, 1/2 mr squared. Okay, so let's solve for, what are we solving for? The torque. Okay, so just move this on the other side of the equation. Torque from that motor is I alpha plus R. Okay, let's do it in multiple steps. So I is 1/2 mr squared alpha. Oh, hold on. I missed one part where it says constant angular velocity. Okay, that's significant. Constant angular velocity means what in terms of acceleration? Acceleration is the time derivative of the angular velocity. So if the angular velocity is constant, what does that mean? The time derivative of a constant is 0, right? Which means I could just cross this out. Okay, so I was kind of rushing, right? I almost missed that part. Constant angular velocity means I can cross this out. So that's nice. So the torque from the motor is actually R times the friction, which is mu k times n. All right, and then we know all those values, right? The radius, be careful, half a meter. The coefficient of friction, I saw it somewhere here, 0.6, and the normal force right here, 40 newtons. Done. Okay, hope that's helpful. Keep on studying. See you in the next video.